that if the disk with center Zj, the largest possible disk with center Zj in omega, Zj plus 1 will be there. What is the use of it? What is the use of doing this? Well, look, let us look at this picture now. You have taken the largest possible disk centered at P, correct? Disk from now means largest possible disk that can be inscribed in domain, alright. Now the Z1 was inside this, right, and the function P is 0 on the first disk, correct. So f of Z1 will be 0 and the disk is an open disk and the function is 0 on the open set, and inside I have taken Z1. So f of Z1 will be 0, f prime Z1 will be 0, f double prime Z1 will be 0. The power series centered at Z1 will be the 0 power series. And so the function f will be 0 on the largest possible disk with center Z1 that can be inscribed in omega. Now repeat the argument. Repeat the argument. And ultimately I will prove that f of q is 0. This is a compactness argument, if you like, whatever that means. All right. So this argument can, you will have to make this argument complete. I need to explain I need to prove to you that this choice is always possible. The choice of Z1, Z2, Z3 is always possible. That is where compactness comes in. You need to use the fact that the gamma, what is gamma? Gamma is a continuous function from the interval AB into R2, and a continuous function on a closed interval is uniformly continuous. The uniform continuity of gamma has to be used in some way. That is equivalent to, or in other words, it's a compactness argument. All right? Yeah?
In that statement of theorem, can we replace that sequence by a subset of omega which contains at least one limit point of omega?
Yes, but omega should be connected. On the connected component, it will be 0.
Then this argument is trivial because we have one disk which contains at least one limit point of that sequence.
Huh?
And our function is 0 on that disk. So it is 0 on all planes. So ultimately it is 0 on.
Not on the whole plane, on the connected component containing the disk, but that is the connectedness argument. You cannot avoid the connectedness argument or the compactness argument. It is not trivial. You have to extrapolate your way from the disk out. Somewhere you have to use extra arguments. Because the point is the domain can go on, it can be amoeba shaped. So you have to go from here to there, step by step, and you're arguing by power series. Power series will only be valid on disks. So you have to go from one disk to the next disk, from the next disk to the next disk. And you have to invoke a compactness argument. You cannot completely avoid it. All right? All right. The next theorem is the Riemann's removable singularities theorem. It's a remarkable theorem actually. It says that suppose omega is an open disk centered at P and f from omega minus P to C is analytic. That is, you take the omega, you puncture omega at a point P, remove a point P from omega, and the function is analytic and bounded. What I am saying is that the function is analytic and bounded in omega minus P, then the limit of f of z as z tends to P exists, let us call it L. You define f of P to be L, the extension is obviously continuous. If I define f of P equal to L, then whatever I get will be a continuous function. It is actually an analytic function. It's actually an analytic function. Now, this is something very specific to complex analysis. There is no such thing available in real analysis. In real analysis, I can have something like f of x equal to sine 1 over x, correct. The function is continuously differentiable. In fact, it is even C infinity on the real line minus the origin, and the function sine 1 over x is bounded by 1, but the limit of f of x as x tends to 0 does not exist, right. So, there is no such corresponding theorem in real variables. It is a complex variables theorem, and you need the Cauchy's theorem for that. Okay. First of all, the extension, whatever it is continuous. If it, we have to of course show that the limit exists, that is a different matter, but once the limit exists, then the extension will be continuous. But what we do directly is the following. Let us define the function. Whether the extension is continuous is really, it is just a comment, it is just a comment, and we begin here, take your gz to be z minus p squared fz when z is not equal to p, 0 and z equal to p, right. Now, you agree with me that f of z is analytic on everywhere except at p. Z minus p squared is a polynomial. So, gz is analytic on, gz is analytic where? On omega minus p, right, because this is analytic and this is analytic. So, it is in particular the only, where will the problem come? The problem will come at p, correct. You have to check that it is analytic at p as well. So, what do you mean by analytic? What do you mean by analytic? It is complex differentiable and the derivative is continuous. Now, we are paying the price for it. You see, for us analytic meant complex differentiable and the derivative should be continuous. As long as the phrase analytic appears in the hypothesis of a theorem, we are happy because we are assuming more. But the moment the word analytic appears in the conclusion of a theorem, we are quite unhappy because not only do you have to establish complex differentiability, now it is our responsibility to establish the continuity of the derivative also. So, this is typically what happens when you change the definition. You may change the definition and make it more stringent, but then when this notion appears in the hypothesis, we are fine, we are safe, but the moment the conclusion contains the word analytic, then we have to prove the analyticity. It requires more work. It is not just sufficient to show that the thing is complex differentiable. All right. So, let us take gz. Gz is z minus p the whole square times fz when z is not equal to p, equal to 0 when z equal to p. Surely gz is complex differentiable everywhere except at p, and at p also you can check by first principles that the g prime p exists and it is 0. Directly you can check g of z minus g of p upon z minus p limit as z tends to p. You can compute this limit, it is 0. Unfortunately, from this we cannot conclude the continuity of g prime. What do we have to show to that continuity of g prime? We have to show that this thing has a limit as z tends to p, and that limit must be 0. The first piece is okay because f is bounded near p, and when z tends to p, this piece will go to 0. This is the problematic piece. Z minus p squared is going to 0, but f prime of z, we have no information about, our hypothesis does not say that f prime is bounded. Our hypothesis only says that f is bounded. It is quite conceivable that f prime may be unbounded and this piece may not have a limit, or even if it has a limit, that limit may be different from 0. So, the continuity of g prime is suspect. We have to prove it. It is our responsibility to prove the continuity of g. All right. So, let us first prove the continuity of g prime. So, we have to show, what do you have to show? We have to show that limit of g prime z as z tends to p is 0 in a roundabout way. We cannot directly, we cannot simply use this to prove the continuity. We can't just, I can't say simply take the limit of this as z tends to p, this goes to 0, this goes to 0, no. It's not clear why this goes to 0. So, you have to do it roundabout. So, here is what we do. See, that's the problem is that it's a complex function theoretic business. So, somewhere ideas from complex analysis has to be used. You cannot prove the theorem without using complex analysis, because it's false for real variables. So, you take the domain omega, you are taking the point P here, and now you are taking a Z away from P, correct? Draw a circle of radius C epsilon, where the radius of the circle is just a little short of Z minus P. If I take the circle of radius Z minus P, then the circle will pass through P. Don't make it pass through P, take a slightly smaller radius so that it misses the point P, right? And then let us compute what is the formula. G prime Z is 1 over 2 pi I integral C epsilon G zeta d zeta upon zeta minus Z the whole square, the formula for the derivative, remember. And what is this? G zeta is what? F zeta into zeta minus P the whole square. What do we have to show? Now, don't forget what we have to show. We have to show this. So, what am I going to do? I am going to take the absolute value of this, and I am going to allow the Z to go to P and show that this is going to be pretty small. That is a simple idea. So, here is your first exercise in this chapter. Exercise, use the integral to show that mod G, so take the absolute value on both sides and work it. Less than or equal to 1 over mod Z minus P minus epsilon into 2 into mod Z minus P plus epsilon the whole squared into maximum of f of zeta over C epsilon. Remember, mod f is bounded on omega, that is the hypothesis. Mod Z is bounded and that is given to you. So, I can take some. So, this f is not a problem here in this integral, this modulus of f is bounded. And zeta minus p, where is zeta moving around? Zeta is moving around on the green circle. What is the distance of zeta from p? What is the maximum distance? Maximum distance is going to be diameter of the circle plus epsilon, isn't it? Your zeta is moving around the green circle. What is the distance of zeta from the center? Maximum distance. It will be when zeta is right opposite, and then the distance will be twice the radius plus epsilon. That small tukda will add up, no? That is what you have here. That is exactly what you have here. And when you parameterize etc., you are going to get this, the minimum distance. You are going to zeta minus z, you take and you get this. So, once you get this estimate, then there is no problem. So, now f is bounded, no problem. So, this in this equation, in this inequality, you let epsilon to go to 0. The left hand side does not depend upon epsilon, left hand side is just z, there is no epsilon coming here. So, you allow the epsilon to go to 0. Once you allow the epsilon to go to 0, you simply get mod g prime z less than or equal to 4 times mod z minus p times this business here, the supremum of f. And so, now you have that as z goes to p, you have the fact that as now you have this inequality, and as z goes to p, gz goes to 0. You have to use Cauchy's the Cauchy integral formula. That is where complex analysis comes in. This is not a theorem in real variables. It is false in real variable theory. So, that will prove for you what? That will prove for you the, where is the, that will prove for you that Gz is analytic. Moment Gz is analytic, G of p is 0, G prime p is 0, the power series expansion for G will not involve the constant term in the first term, and so you will get Gz equal to z minus p the whole squared times Hz, where Hz is analytic, and this is equal to z minus p the whole squared into Fz. The z minus p the whole squared cancels out, you get Fz equal to Hz, and Hz is analytic. So, the argument is, I asked you to complete the argument, use the integral to show that it is bounded, and as so now you complete the argument. Complete the argument. Your Gz will be equal to z minus p the whole squared times something, which is equal to z to Hz, right, which is equal to z minus p the whole square into Fz. Try it out. The next theorem, sorry, this is a somewhat theoretical lecture, but somewhere you have to learn some amount of theory. I mean, and the proofs are well chosen. I have chosen these theorems to illustrate the power of the Cauchy integral formula. That is why these theorems are being done, because in every one of these proofs the Cauchy formula is being used again and again and again and again. Alright. The maximum modulus theorem. Once again, there are several proofs of the maximum modulus theorem, and I have chosen that proof which emphasizes the Cauchy formula. It is one of the most beautiful proofs of the maximum modulus theorem. Maximum modulus theorem says that suppose f from omega to c is analytic, where omega is a connected open set, and if mod fz attains a local maximum in the interior of omega, then f is constant. An analytic function, the modulus of an analytic function cannot attain a local interior maximum. Okay? It cannot attain a local interior maximum. So, assume that mod fz attains a local interior maximum, say at the point p in omega. Well, what is the meaning of saying that it attains a local interior maximum? What is the meaning of the statement? That means that it is a maximum in a small neighborhood. So, take a small disk of radius r centered at p. You have this is your omega. It attains a local interior maximum at p, which means that it is a maximum in a small disk around p. Is that right? Is that what the meaning of local interior maximum means? That means that there is a mod f of z is less than or equal to mod f of p in this small disk of radius r centered at p, correct? Alright. What is the next step? Apply the Cauchy integral formula for the circle with center at p. So, what is the formula? What is the Cauchy integral formula for a circle at center p? F of p equal to 1 over 2 pi I integral f zeta d zeta upon zeta minus p. And you might try to work with this formula and try to get the result. Not quite. You need to be slightly cleverer, and this proof that I am going to give you is due to Edmund Landau. It is one of the most beautiful proofs of the maximum modulus theorem. you should look at this book, Polya and Syzago, Problems and Theorems in Analysis. Polya and Syzago, Problems and Theorems in Analysis. Problems and Theorems in Analysis. I think it is volume 2 on page 30 of this. You should look at Polya's comment on Landau's proof of the maximum modulus theorem. I will just leave it to you to read Polya's comment on this theorem. Syzago, Szego, O with 2 dots on it, the O umlaut. Problems and Theorems in Analysis. Look at volume 2, page 30 for his comment. So now let us apply Cauchy's integral formula not to f but to fz to the power m. Apply it to this function, and then what do you get? You get fp to the power m equal to 1 over 2 pi I integral mod z minus p equal to r fz to the power m dz upon z minus p. Differentiate with respect to p. This formula is true regardless of whether the local maximum is attained at p or not. This is a general formula, true for any analytic function f. So differentiate with respect to p, and then you get m fp to the power m minus 1 f prime p equal to 1 over 2 pi I times this. And now take absolute values. Now take absolute values. Your m into mod of fp is the maximum. M to the power m minus 1 into mod f prime of p less than or equal to parameterize. You are applying a disk. You are applying it over a disk. 1 over 2 pi times integral of the modulus. Parameterize. What are you going to get? Parameterize the disk. You are going to get m capital M to the power m minus 1 f prime of p less than or equal to 1 over 2 pi 0 to 2 pi. Remember that mod fz is less than or equal to mod fp, and mod fp is m, right? And then dz, dz is r dt, I r e to the power I theta, I r e to the power I t dt are taking the modulus, it's gone. Z minus p is r e to the power I t. So you are left with an r squared. All in all, the m to the power m minus 1 cancels out, and you get f prime of p is less than or equal to capital M upon Rm, and the little m was absolutely arbitrary, and I can allow the little m to go to infinity, and I get f prime of p is 0. Alright. Now take this equation again, start out with this equation. No, not this one, excuse me, this one. Start with this one and differentiate it again with respect to p. Once differentiation give you this, differentiate this again with respect to p. You are going to get the f double prime term now, and repeat the argument and show that f double prime p is 0. Again differentiate and show that f triple prime p is 0. The power series for f centered at p reduces to a constant. So in a disk of radius p, in a disk, small disk centered at p, the thing is a constant, and again you have to use a connectedness argument or whatever it is, and you have to show that it's constant everywhere. Is it clear? Please read this very carefully and follow the details of this argument, because it's one of the most beautiful proofs of the maximum modulus theorem. It's very clever argument. A simple idea, the Cauchy's integral formula is used not only for f but for all the powers of f. So the idea, the entire potential, is used, and you are getting better and better results. You are bootstrapping your way up. Some exercises. Show that hyperbolic secant x, hyperbolic secant y upon 1 plus x squared plus y squared is not harmonic. It is not the real part of an analytic function. Of course, you could try to calculate the Laplacian, but you are going to get into a miserable, horrible mess. Don't try to calculate the Laplacian. First, do this part. Show that if u is harmonic and non-constant, then u cannot have an interior maximum. A harmonic function cannot have an interior maximum. This is the maximum principle for harmonic functions. Those who are doing PDEs, take note. This is a harmonic function. A maximum principle for harmonic functions is one of the most important ideas in the theory of partial differential equations. The hint is e to the power f is x of real part of f. Apply the maximum modulus theorem to e to the power f. Apply the maximum modulus theorem to e to the power f. And some routine questions like find the apply the maximum, examine the function mod x of z squared in the light of the maximum modulus theorem. Maximize mod x z squared on the unit disk. So we can do these questions. So let us finish this classification of singularities. I know that it's getting a little lengthy, but let us just finish this whole thing before calling it off. Still 5 more minutes, maybe perhaps. All right. Or you want me to stop here? Tired? All right. Let's stop then. Let's just call this end of chapter 6. Let us then call it the end of chapter 6.